I'm here doing some examples from 10.1 and 10.2. More from 10.2 because I know we kind of rushed at the end with the geometric series stuff, so I want to make sure you guys are, clear with, excuse me, you guys are good with geometric series. So why don't we just jump right into 10.1? Just a quick reminder, none of this is going to be on your midterm. So if you're watching this before the midterm, maybe save it after. All right. Maybe save this for after the midterm so that you can focus more on studying. Okay. All right. So 10.1 was on sequences, and I kind of made it a really big point that sequences and series are very different. This is something that you're not really going to see in this class, but it's something that I thought was kind of cool, and thought it was kind of relevant to what we talked about today. So we're looking at example 11 on page 559. And basically the prompt goes, they give you a sequence. It's 3n over n plus 1. And they're saying to apply what we just learned. I'm sorry, apply a theorem that we talked about in class to an actual function. They define a couple of things. They say f of x is equal to e to the x, g of x is equal to x squared, and they're saying like what they're asking you to do is compute f of a sub n and g of a sub n when you take the limit as the sequence goes to infinity. Okay, so what that means is you want to find the limit as n goes to infinity of your sequence first, and then what that's going to do is it's going to spit out a value of, assuming that it converges, and that you can plug into the function. And this is what I was trying to say before, right? Like that the limit operator can like flow in between a function or outside of a function, right? So why don't we compute this first using what we talked about in class, right? Let's do that trick I said. Let's divide by the highest power and see what we get. So it looks like if I divide this by, I'll do it in red. If I divide this by n, divide this by n, divide this by n, I'm left with the limit as n goes to infinity of 3 over 1 plus 1 over n. And we can see that this piece is going to go to 0, leaving you with 3. So what this is saying is like this chunk right here is tending to 3 as n goes to infinity, right? So if I have f of x, well, I guess f of a sub n, right? And I want to take the limit now as n goes to infinity. Like since this is the same thing as f of limit as n goes to infinity of a sub n, right? This is the same thing as f of 3, which is e cubed. All right? So it's a little bit more explicit in terms of like showing like how we got to like the final answer. Yeah, some of you saw it right away and was just like, oh, that's just e to the 3, right? But this kind of shows the middle step of like how we're using limit law to kind of evaluate this, right? And then similarly, if we do the same thing with g of x, right, we get g of limit as n goes to infinity of a sub n, and that's the same thing as g of 3, which is 9, x squared, 3 squared, which is 9. All right, so I thought it was a nice little example that kind of tied everything together, right? The stuff with the limits, the stuff with the sequences, using limits to prove convergence or divergence, and then even using the preservation law with limits under function operations, okay? All right, so there's that one. What else were we doing here? We're doing, the telescoping one, all right. So we're jumping to 10.2. And we're doing, I think it's the first example in the book. It looks like, so we're talking about series now. We're going from 1 to infinity of 1 over n times n plus 1. All right. So if I look at this guy right here, if I kind of look at it all at once, this is going to look like 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus so on and so forth. And actually in this form, it's kind of like we're not sure what's going on. All right, we're not really sure what's happening here because, well, I didn't really teach you the other rules yet, but so yeah, I wanted to show you this one because it actually has its own name. It's called telescoping series, and you're going to see why it's called telescoping in a second. So in this form, right, the way it is right now, it's kind of like ambiguous, right? We're not really sure. So what we're going to do is actually rewrite this. In fact, we learned how to rewrite this, right? Hopefully you guys see it. It's a partial fractions, isn't it? This is the same thing as 1 over n minus 1 over n plus 1. If you don't believe me, you can do the partial fraction stuff on your own, right? That's like the whole like a over n plus b over n minus 1. You choose your n's and blah, 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 right? So you can use the same thing. I promise you get to this answer. And now that it's in this form, right, we can kind of rewrite this. 1 over n minus 1 over n plus 1. And we get something that looks like a little different here, right? If I plug in 1, I get 1 over 1 minus 1 over 2. So this is for I'll highlight it, or I'll accentuate. This is n equals 1, the n equals 1 term. Then we do the n equals 2 term. We get 1 half minus 1/3. Once again, this is the n equals 2 term. And then we keep on going here. We get 1/3 minus 1/4. And maybe some of you see it already. N equals 3. Something interesting happens here. We see like this pattern that starts to emerge, right? Like this term, this negative 1/2 is going to cancel out with the 1/2. This negative 1/3 is going to cancel with the 1/3. The negative 1/4 is going to cancel out with the following positive 1/4. And we kind of see like there's this like leftover, there's always going to be like this leftover second term, right? I'm going to highlight it here. It's like this term is the only one that's going to survive, along with the like the end term of the last, I guess like piece, right? Partial, they call it a partial sum, right? And what ends up happening is like the middle piece kind of just collapses like a telescope. That's why they call it a telescoping series. The middle piece is going to end up collapsing, and you're actually going to be left with this 1 minus 1 over, they use a capital N because like it represents a really, really large like n value, right? And there's a theorem that basically says how to compute a series. It basically says to look at what happens when the limit as this thing goes to infinity. And here's the cool thing, since we're taking the limit of the partial sums, you're going to hear that a lot, limit of, it's called the partial sums, right? Since we're taking the limit of the partial sum and we get something that's convergent, this is actually going to be what the series itself converges to. So yeah, the answer for this one, so kind of going back, or let me just rewrite it here. This is equal to sum of n equals 1 of, what was the original problem? It was like 1 over n times plus 1. So not only are we able to show convergence, but for this one, but we are actually allowed to show what this one also converges to, kind of like geometric series, right? We found a way to cancel enough of the terms so that the series will converge. So converges to 1. That is the ugliest one I've ever written. Okay, converges to 1. Okay, so I thought this was a pretty neat example. This one's not going to be on the midterm or the final. I just thought this was interesting, and I saw this a bunch of times when I was taking calc also. All right. The last couple of examples are all going to be geometric. So if you are good with geometric series for whatever reason, you really don't need to watch this part. But if you want to see the extra examples, by all means, follow along. This is example 4 on page 569. All right. So we said in class that it has to start at 0. It can start at 1 also. In fact, I will explain. Oh, wait, no, this one's perfect. This one doesn't start at 0. Awesome. So I'm going to explain how that affects our stuff at the our equation, okay? This one, it actually starts at 3 and goes to infinity, and looks like this. You also notice that the r value is negative on this one, right? So what does that mean? Does that mean like we have to put a like negative in the formula or a positive in the formula? So we have to check if the r value, the absolute value of r value is less than 1. So long as this is true, we can say that this converges. Oh, I forgot. And this is geometric, right? Ugh. Sorry. So I said in class, you need to say 2 things for you to show convergence or divergence of a geometric series. So this is geometric with a is 7 and r is -3/4. So that's the first thing you need to state. And the second thing you need to state is, since the absolute value of r is less than 1, so I'll write since this, the series will converges. So we're partly done. We've decided, we've determined if this converges or diverges, but now the question also asks you to evaluate. Meaning, what does this sum up to, right? So we're going to need to use our formula. We're going to need to use our formula for this problem. Now, I just realized I kind of misspoke in the lecture and here. So this actually is not true. Although it looks like our form, that we talked about in class, because the index starts a little ahead, it doesn't start at 1 or 0 anymore. Because it starts a little ahead, the a value, which represents the first term, actually changes. So this is kind of like a curveball for a lot of reasons, okay? The r value is the r value. It is -3/4. But the a value is not 7. Because watch, if I string out the first couple of terms of this series, I plug in 3 first. I get 7, and then this guy, I'm just going to leave it in this form, and then plus 4, right? N equals 4, plus, and so on and so forth. Notice this guy, this first term in the series is not 1. Or I'm sorry, it's not 7. It's 7 times blah, 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 right? So make sure, this is kind of important, make sure you take note of this. I really underestimated this example. This is a good example. All right, so when we use our formula now, right, when we use our formula now, it's a over 1 minus r. A value is going to be this guy, 7 times all that nonsense, right? So it's going to be 7 times -3/4 to the third over 1 minus -3/4. So that's going to be the setup to our sum. All right, and then the rest is just algebra. You just compute it out. 7 times what is that? -3 cubed. I think that's -27 over 4 cubed, which is 64, all over 7 over 4. That's a negative sign. I think that's right. And then oh cool, the 7s cancel out. Looks like the 4 is going to cancel out with the 64. Leaving you with, oh my gosh, 116. Yeah, okay. And then so that means you're left with -27 over 16. Oh, look at that. All right, so that was example 4. Once again, look out for your index. Your index is really, really important. Okay, it's a small number, but it has a big impact. All right. All right, example 5. Example 5 is I like this one. Okay, so they're saying give the fractional representation of 0.21 repeating. 2121 dot 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 dot. Give the fractional representation of 0.21 repeating, right? Without a calculator, obviously. And in fact, this can kind of explain what calculators do to turn repeating fractions into decimals, right? I know you guys are used to pushing the math frac button in your function button in your calculator, but we're going to use series to actually, geometric series to prove it. So here we go. I notice that this is repeating every 2 terms. So if I want to turn this into a kind of like a series, I can look at the first 2 terms, right? So that's going to be what is that? 21 over 100, right? Because that's 0.21. This represents 0.21, right? And then I can add it to 21 over. I think that's right? Because I just tacked on 2 zeros, so that gives me like the next 2 spots in the decimal. Does that make sense? Yeah, I think that makes sense. I think I said that right. And then this is going to actually follow the same pattern, right? I just need to tack on 2 zeros every time I go, right? So and then 1 2, and then that gets me that. And you start to see a pattern emerge, right? This is going to be plus 0.000021. You're going to start to see a pattern emerge, right? This can be rewritten as 21 over 100 to the n power. No, that's not right. To the 100 to the... No, that is right. Right? Yes. With a sum, and we go from 1 to infinity. Right? Yeah. Because if I plug in 2 into this, I get 10,000. And then if I plug in 3, I get 1,000,000. Yeah, so this works out. And look at this. This is a geometric series where my first term, I actually found it already. This is A. And then my common ratio, my R, is it looks like 1 over 100, right? Because I can rewrite this as 21 times 1 over 100 and sum from 1 to infinity. Right, so my common ratios are, and just like that previous example, okay, this is not my A. This is not equal to A. A is the first term of the series, right? So R is 1 over 100, and I can actually now turn this into a fraction, right, using A over 1 minus R. So A is, what did we say, 21 over 100 over 1 minus 1 over 100. Do some simple algebra here. 21 over 100 over 99 over 100. Hundreds cancel out. And look at that. You just fracked it. You turned the repeating decimal into a fraction. Whee! Pretty cool, right? You can do that with any repeating decimals, okay? And then the last example I wanted to show you guys. This video is starting to run a little long here, but it's example 7 on page 570. I'm just going to do the setup, and you guys can finish off the problem. This is the sum from 0 to infinity. So it starts at 0, okay? Take note of that. Of 2 plus 3 to the n over 5 to the n. And at first glance, you look at this and you're like, well, this doesn't look geometric. It kind of looks geometric, right? If only we could separate it. And we can, right? We can because the addition's on top and not on the bottom. So we're going to rewrite as 2 separate series. So I didn't really explicitly say this during lecture, so I'll say it now. You can split up series into multiple series. It's like saying, like, if I have the sum of a sub n plus b sub n, this is the same thing as the sum of a sub n plus the sum of b sub n. You're allowed to split them up. Addition and subtraction is preserved under series, okay? Kind of with limits. All right, so we can rewrite this as n equals 0 to infinity. And this should kind of look familiar, right? With like the integrals and stuff. I mean, integrals came from series, right? So anyways, we get, what is this? 2 over 5 to the n plus the sum of n equals 0 to infinity of 3 to the n over 5 to the n. Remember when I said in class you need to know your exponent rules? This is why, because you can rewrite this as 3 over 5 quantity to the n. I just did the exponent rules backwards. And then, I'll rewrite this first one too. This becomes 2 times 1 over 5 to the n. So what does this mean? This means there's 2 problems for you to do. It's like a 2-in-1. Okay? You're going to prove the convergence of the blue and tell me what it sums up to. Add it to the convergence of red and tell me what it sums up to. Okay? I'll leave that to you guys to do. All right? This is my gift to you guys. All right? And so you guys can enjoy that. It's also in the book. I said it before. It's on page 570. So if you want to check your work, it's all there too. All right. So that's it for this one. Please study for the midterm. And if you're watching this after the midterm, then I'll see you next class.